Okay, in this question, we have a system of forces which we're going to call system A. And we want to do two things. We first of all want to replace that system of forces with an equivalent system. And our equivalent system has a single force and a moment, both applied at the origin. We then want to take our system and we want to replace it with an equivalent system that is simply a single force. Okay, so without a directly applied moment. So the first thing to acknowledge when we're trying to determine equivalent systems is that the sum of the forces, if we have system A, which is a system we started with, we can say the sum of the forces in system A must equal the sum of the forces in our equivalent system, which we're going to call system B. And we also have to have moment equivalency. So we're going to say that the sum of the moments in system A must equal the sum of the moments in system B. Okay, so that's what we're going to use to determine our equivalent systems. Now, it's worth stating at this stage our sign convention. So for moments, a positive moment will be a clockwise moment and a negative moment will be an anti-clockwise moment. For forces in the x direction, horizontal forces, we will say that forces to the right are positive and forces to the left are negative. And for forces in the vertical direction, we will say that forces upwards are positive and forces down are negative. Okay, so it's important that we have a good, clear understanding of our sign convention before we embark on a problem like this. So we're going to first of all think about determining the horizontal force in our equivalent system B. So in order to do that, it's simply going to mean what we're simply going to do is we're going to take the sum of the forces in the system that we have in the x direction. So for system A, in the x direction, we're going to evaluate the sum of the forces. And that will essentially equal the horizontal force in system B, our equivalent system. Okay, so that's the first task. So looking at the system of forces again, we're going to have to determine the horizontal component of each force. So we've got this guy, the horizontal component of the 75 newtons, the horizontal component of the 100 up top, the horizontal component of the 100 at 45 degrees down below. And we note that the moment out here has no effect on the force equation. Okay, so let's rattle through this fairly quickly. So what have we got? We have 100 times the cosine of 20 degrees, and that's positive to the right. And that all equals fxb. Okay, and so we can evaluate fxb equal to fxb. When we evaluate the numbers, it's equal to 48.91 newtons. Okay, all right then. So now we can go ahead and consider vertical force equilibrium. So doing the exact same thing, we're simply saying that the sum of the forces in the y direction for, for system A, well, that's actually going to be the vertical force, the equivalent vertical force in system B. Okay, so what do we have? FYB is equal to minus 33.97 newtons. Okay, the minus is telling us that according to our sign convention, it's acting downwards. Similarly, for the horizontal force, the positive is telling us, the fact that it's a positive number tells us that it acts to the right. Okay, so now we have worked out what the equivalent force in the x and y direction is for what we're calling system B. Now, we have to bear in mind that those are the two orthogonal force components. But we want to get the resultant force. So we can use the geometry of a right angle triangle to tell us what the resultant force is. If we simply sketch out fxb equal to 48.91 and fyb equal to 33.97. You'll notice I haven't put the minus sign in here because the direction of the arrow is indicating the orientation of the force. So we have a right angle triangle. Okay, so we know that the resultant force is going to have a magnitude equal to the length of this line. Okay. So let me see. We have the resultant force for force B is equal to the square root of fxb to be squared plus FYB. Okay, because that's our right angle triangle to be squared, Pythagoras' theorem. Okay, when we put the numbers in, we're going to have RB equal to 48.91 squared plus a negative 33.97 squared. Square root of all of that gives me RB equal to 59.55 kilonewtons. Okay, now we've determined the magnitude of the resultant, but what we actually want to do is determine the angle at which it is orientated. So it's somewhat misleading to draw that like that. I don't need to invoke the image of a right angle triangle anymore. I can actually draw the resultant. I can draw the resultant in its correct orientation. So the resultant of those two forces will be a force that looks like this. Okay, and I want to determine this angle theta. Okay, so again, simple geometry will tell me, let's call it theta subscript b. So theta b is going to be the inverse tan 34.8 degrees, and it's important to state that that is clockwise from the positive x-axis. Okay, excellent. So now I've fully defined the force, the equivalent force in system B. So I have the resultant and I have the orientation of the force. Now, the next part of the question is to determine moment equilibrium. Okay, so it's not, we have not fully defined an equivalent system yet. All we have established is force equilibrium. What we now need to establish is moment equilibrium, because all of the forces in this system, all of the forces and indeed the moment applied in system A may well have a moment effect about the origin. Okay, so a torque or a rotational effect about the origin, and I need to determine what that is. So following exactly the same procedure that we've used for forces, we can say that the sum of the moments for system A, that's going to equal the equivalent moment in system B. Excellent. So let's take moments about the origin. So taking moments about the origin, MB is 285.39 Newton meters. Excellent. Okay, so now we're at a position where we can fully define system B. We can take the four forces on one moment that were applied at system A, and the equivalent system has a force, a resultant force, like so, with a magnitude of 59.55 newtons, and that's at an angle of 34.8 degrees. But we must also account for a clockwise moment. Remember, we have a positive number, which means we have a positive moment, 285.39 Newton meters. Excellent. And this is system B. So for the next part of the question, we need to replace system A with not a moment and a force, but actually only a moment. Okay, so that essentially amounts to taking what we have called system B here and replacing this with a single force positioned somewhere along the x-axis. So essentially what we're going to have to do is use the vertical component of this force to generate our clockwise moment. Okay. So in order to do that, we're going to take the moment that we need to generate. So I need a moment of 285.39 Newton meters. I need to generate that moment. Okay, I can't directly apply it like I have in system B. So I must essentially generate the moment using the vertical component of this force, 59.55. So essentially take the moment that I need to generate and let that equal to the vertical component of the force that I have at my disposal, 33.97, Okay, and that gets multiplied by a lever arm, which we will label dx. So this vertical component times some lever arm dx, which I need to find, equals the moment that I need to generate. So that simply allows me to determine dx equal to 8.4 meters. Okay, let's call that system C. Okay, so what does system C look like? This is system C, which is completely equivalent to system B, which is completely equivalent to system A. System C, okay, because it's the vertical component of that force, of that 59.55, that is now generating my clockwise moment of 285.39 Newton meters.